All right, so the question asks us to define the ohm. Now, whenever they say define, they're usually talking in terms of the formula or the expression, right? Because that's how any physical quantity is defined using a mathematical expressions, right? Now, they're saying ohm. We know ohm is a unit. It is not a quantity, it is a unit, and it is a unit of resistance, right? Now, what is the equation for resistance? The equation is defined basically also using Ohm's law that relates the potential drop across a resistor via this equation. And you can rearrange this equation to get R equals V by I. Now we know the units for V by I. For V, it's voltage, volts. I is current, so it's amperes. Which means that the ohm is defined as the ratio of volt per unit ampere, right? So you can say it's volts per unit ampere. So that's ohm. Part B, a wire is made of metal of resistivity rho. The length L of the wire is gradually increased. Assume that the volume V of the wire remains constant as its length is increased. So we are just assuming, so this is the wire. And its length is increased slowly, gradually, but they're saying that the volume remains constant. Show that the resistance R of the extending wire is proportional to L squared, right? So if it is L, the length is L, which is gradually increased as well, we have to show that the resistance R is proportional to L squared, right? So, and we know resistivity as rho. So we have an expression that defines the resistance on how it depends on the material. So rho, it depends on the resistivity of the material, it depends on the length, and inversely on the area. This is the expression for resistivity. And we know that volume is defined as the area, the cross-sectional area of the wire times the length of the wire, right? Which I can rearrange to get an expression for A in terms of L and V. So this gives me V by L. So now if I put this back into this expression, this gives me R equals rho L by V by L, which is just rho L goes upstairs, L squared divided by the volume. And from this equation, we can clearly see that resistance is proportional to L squared. Moving on to part C, a battery of electromotive force e.m.f. E and internal resistance small r is connected to a variable resistor of resistance R. So here we can see the circuit diagram. This is the battery. It has an EMF and it also has an internal resistance which is connected through this variable resistor, and you can see that to measure the current we have an ammeter, and the potential drop across the resistor can be measured using this voltmeter. An ammeter measures the current I in the circuit, and a voltmeter measures the potential difference V across the variable resistor. Now the resistance R is now varied to change the values of I and V. So you vary the resistance, that means different amounts of charges or current will flow through that resistor. The higher the resistance, the less the current flows, and that also determines the different variable potential drops across the resistor. Now the variation of I of V is shown in this figure. As you can see, here we have the potential difference, we have the current, and it is a decreasing gradient straight line. Now they're saying use this figure to state the EMF of the battery. Now the EMF of the battery, right, it is obtained when there is no current flowing through the circuit. Which means the current flowing, when it's zero, that's when you have the total EMF of the battery. And the current is zero on this axis, voltage axis, and we can see that this line would be, this point would be the total EMF. So this is 2.1234, so it's 2.4 volts. So the total EMF of the battery from there is 2.4 volts. Next, use the figure again to determine the power dissipated in the variable resistor when there is a current of 5 amperes. Now, obviously, when there will be a potential drop across the resistor, the potential is dropping. So the total power of this resistor would be decreasing, right? The power would dissipate through the resistor. And we know that the power dissipated is given by P equals VI, where V is the potential drop across the resistor and I is the current that flows. Now, they're saying when the current flows is 5.0 amperes, what's the power dissipated at that time? So we'd want a value for voltage corresponding to this 5.0 amperes, and we can use the figure to determine that. So this is 5 amperes, and this would be the potential drop at 5 amperes, which is about 1.3 volts, right? So this is 5.0 amperes. So the potential drop for 5 amperes is 1.3 volts. So this gives me the power dissipated as 1.3 volts into 5.0 amperes, which is just 6.5 watts. So this gives you the answer 6.5 watts. Right. Now, they're saying state what is represented by the value of the gradient of the graph. So if you look back at this graph, the equation for an EMF connected across a variable resistor, or any resistor where the battery has an internal resistance as well, we know that the equation for that is defined as E equals IR plus IR, where I is the current that flows through the battery and the circuit. Small r is the variable, it is the internal resistance of the battery, while capital R is the variable resistor. So this is the equation for our circuit that we have in this question. Now we know that IR is just V, right? So this is the capital IR plus, so this is just V. Now we can rearrange this equation as R is equal to E minus V divided by I, where on the top we have the vertical, what we have here on the vertical axis, and on the bottom we have what we have on the horizontal axis. And that's how the gradient is defined, right? So the gradient, which is normally written as M, it is defined as change in Y by change in X. So which means that this internal resistance is the gradient of this graph. Therefore, it is the internal resistance that is represented by the value of the gradient of the graph.